Today let's talk about a very famous algorithm in computer graphics, and one that's been there for almost forever in computer graphics terms. It's been popularized in the early 70s with a variation on it called Conway's Game of Life. Today I want to talk about cellular automata. So let's look at a simple case first. And a cellular automaton is not very different from a kernel in that it looks at neighboring cells in a grid. So we're currently working on this cell here, and each cell can have two values. Either they're dead and have a value of 0, or they're alive and have a value of 1. Now let's make up some rules here and say if a cell is dead, it will come to life if it has exactly 4 live neighbors. And on the contrary, if a cell is alive, it will only survive if it has exactly 4 neighbors. So in our case, that means that our dead cell will come to life because it has exactly 4 neighbors which are alive. It's those 4 neighbors here. So our cell comes to life. Like so. Apart from this very simple cellular automaton model that we just looked at, there's another model, more intricate, and it's called a multi-state cellular automaton. And it works like this. First, let's allow more stages than just being dead or alive. And let's also introduce some stages in between being alive or dead. Let's call them limbo. In our case, we allow for 5 different states: 0, 1, 2, 3, and 4. As in our previous example, a cell with a state 0 is dead. However, to be alive, a cell has to have a state 4, and a cell with a state value between 1 and 3 is in limbo. So again, 0, dead, 4 alive, 1, 2, 3, limbo. And let's use the exact same rule as previously. A dead cell with 4 alive neighbors will become alive, and a live cell only survives if it has exactly 4 live neighbors. In our case, the cell that we're working on is dead, and it has exactly those 4 neighbors here that are alive, that have a value of 4. So the cell we're working on becomes alive. Let's look at a case when our cell is alive. So it has a value of 4, and it does not have 4 neighbors, which are alive. So only these 2 neighbors here are alive. In this case, we just lower the cell's value by 1. So instead of a 4, it now contains a 3. Finally, let's look at this cell when it's in limbo, when it has a value of 1, 2, or 3. Now if this cell is surrounded by 4 live cells, 1, 2, 3, and 4. In this case, our center cell's value does not change. This case is called survival. In order to build this, we will start out by creating 2 volumes. And let's just use 1 volume sub here for that. Let's just increase the sampling, divisions, and call this one A. And let's just append a name sub. Call this one B, wire this into the volume, and merge it. So we now have 2 volumes, one called A, one called B, of identical size. And after that, let's drop down a volume wrangle to initialize the values in our field here. Let's just check if the distance between our current voxel position and the origin of 0, 0, 0, if that distance is smaller than, say, 0.15, and only then we'd like to set the value of A to 1.0, like so. Let's highlight this, and we see we have a sphere here of values of 1.0. Let's dial this radius a bit down, like so. Next, let's drop down our OpenCL. And what I want to do here first is bind those 2 volumes. So I'll bind a parameter called A and one called B. Let's fold these down here, and both should be a volume with our first volume called A and the second one called B. We want to uncheck force alignment on our first volume, want to make this writable, and want to make our B volume writable as well. In the Options tab, we will run over the first writable volume, and finally in our kernel, we check Use Code Snippet, use Writeback Kernel, and we generate a kernel. Let's select all this, right-click on it, copy text, and say OK. Also, let's directly create the Writeback Kernel by just copying this and pasting it down here and setting its name to, let me just check, Writeback. So that it matches the Writeback kernel name here. No errors in our OpenCL, that's good. So back to our code, and up here the first thing I want to do is read out the value of the voxel that we are currently working on. So let's cast this to an integer, Let's call it val, and we want to read out our a volumes voxel at the index, idx that is. And we just calculated this index up here. Next, we want to look at the adjacent voxels and see if they are alive, so if they have a value of 0 or 1. And I'm just going to take a shortcut here and open up our previous file that we created when implementing the kernel in OpenCL or the reaction diffusion. So this is the code from the reaction diffusion tutorial, and what I want to copy is this up here. So these 3 nested for loops that go through all the neighboring voxels. Let's just copy this, and in our new file, let's paste it here. And for now, except for the line where we sample the surrounding voxels, I want to delete everything else. And let's also cast this to an integer and call it nayval for neighbor value. Now I need to count how many of these neighboring values are 1. So in order for that I need a counting variable. So let's create one, call it sum, and initialize it to be 0 in the beginning. And after we sample the adjacent voxels here, let's check if the neighbor value is bigger than 0, so if it's 1 in our case. And if so, let's just increase the sum by 1. And I can write sum plus plus for that. So now after I summed up all my neighboring values, I want to check first if my current center pixel is alive or dead. So if center pixel's value stored in val is bigger than 0, and if we have exactly 4 adjacent voxels being alive, so if sum equals 4, then this voxel stays alive. So nothing changes here. But if this is not the case and we don't have 4 neighbors which are alive, then our current voxel dies. So we'll set its value to 0 by setting a at our current index to 0. And if the value of our center voxel is not greater than 0, so if the voxel is dead, then we check if the sum again equal to 4, so if there were 4 alive neighbors. And if so, we'll set our current voxel's value to 1, so it'll become alive. So in theory, this was all the code that's needed for a simple cellular automaton. However, to avoid race conditions and conflicts when executing OpenCL, we'll have to make sure to write these results into a temporary volume and then use a write-back kernel to write back those values into our main volume, as discussed in the 2 previous lessons. So up here, let's introduce this temporary volume, and we're just going to use volume B as a temporary volume. So B idx should in any case be equal to our A volumes value. And down here, instead of changing our A volumes value, let's just change the B volume value directly. And down here in the write back kernel, we will just write back the values that we saved in B into A. So our volume A's voxel equals our volume B's voxel. Like so. Okay, good time to save this. Let's throw this OpenCL wrangle, let's just cut it and throw it into a solver. Wire this up here, go up one level, highlight the solver, and after that maybe drop down a volume visualization and increase the density scale to say 100. So we can see some interesting patterns emerging here. And let's save this and hit play. And we see this is not really stable, this just goes away. So let's tweak our initial conditions here a bit. In the volume wrangle, for example, let's maybe decrease the radius of our initial sphere here, and that does not help really. So how about instead of setting those values by the distance from our center, let's just set them randomly. So we'll check if our random generator, just going to use inRandom here, is smaller than 0.1. So in 10% of the cases, I want to set our ace value to be 1. And that looks rather promising. And you can see this is just flickering around and we can see no clear system in here. So let's maybe dial down the probability for a cell to become 1 even further and hit play again. And you can see now it's got this weird emerging behavior. Maybe dial down the probability a bit more. Yeah, we can see something like this. So this simulation behaves like a weird organic growth of some geometric weird form. And maybe let's combine those two. So we'll say if the distance to the center is smaller than 0.5 and with a probability of 0.5%, we set our cells to a value of 1. Yep, and now we get something going here. Okay, you might say this is not really useful. And I partially agree, because it always will yield these weird behaviors. So how can we get other behaviors? Well, by simply changing our rules. So a rule is defined as how many neighbors should be alive in order for a given voxel to survive or become alive. So in our case, for a voxel to survive, it needs 4 live neighbors. And if our voxel is dead, it needs 4 live neighbors to become alive. So what if we change those, for example, to be 1 by 1? So it only needs 1 neighbor to survive and 1 to become alive. Let's head up 1 level, and we immediately see this is really getting crazy. But maybe if we just stick with this single sphere, we can see this yields those weird geometric patterns here, which are very symmetric. Let's maybe decrease the size of starting sphere here. We can see now we get these typical patterns here, which are flickering fast. Okay, again, maybe for abstract art, why not? But what else can you do with a cellular automaton? Well, you can turn it into a multi-state cellular automaton, and thus greatly increase the patterns and the behavior of the whole system. So let's do that. Dive into our solver. Let's call this OpenCL Wrangle simple CA for simple cellular automaton, and copy it over and rename it to multi-state CA. So that's the one we're going to be working on. What I want to introduce up here is another integer which stores the number of allowed states. And in our example, we allowed 5 states. So 0, 1, 2, 3, and 4. And down here, where we previously checked if the neighbor's value was greater than 0, so if it was 1, we now have to check if the neighboring value equals 2, and let's call this states. So if this neighboring value equals to a value of states minus 1, again, if we have 5 states, the number 4 will be the highest value. So if our neighboring value in our case is 4, then we increase the sum. And down here, for the case that our voxel is alive and it has not got enough neighbors to survive this iteration, we previously just set its state to 0. However, in our case, we want to set it to its previous value minus 1. And down here, if the voxel has been dead and we found enough neighbors to resurrect it, we set its value to, in our case, 4, but let's keep this procedural. So in our case, the value will be the number of states minus 1. So it'll be alive. So we have 5 states here, and let's set the number of adjacent voxels that are needed for survival to 4, and the number of voxels for resurrection to 4 as well. Again, save this, go up 1 level, highlight our volume visualization, and hit play. Not much happening there. That's because these systems are kind of finicky when it comes to initializing their values. So I maybe randomize those values, and of course I will have to set them to 4 in our case, because as we have 5 states, a value of 4 will indicate that a voxel is alive. We can see now we get behaviors like this, which are much more interesting, much more organic. And maybe let's get rid again of the noise here. We can see now we have behaviors like those. So that is a multi-state cellular automaton. And as we often get the question, how do you come up with that stuff, or where do you find your sources and how do you find them? Let me take you through the process that led me to this code. And it was quite a struggle because there is lots of info on standard CAs. However, it turned out to be really hard to find any decent info on multi-state CAs. So what I did, of course, just started by Googling out cellular automata. And as we're in Germany, of course, I find the Wikipedia page in English as well. There's a giant section on cellular automata on Wolfram's Math World, and this is the normal behavior, the normal images that you get from standard 2D cellular automata. Now when you're Googling 3D CAs and go to the image search, you find lots of references here. And what actually got me further was this video here, Jason's Brain 3D Cellular Automaton. And this looked quite interesting. So I clicked on the username that uploaded this, and it's called Softology. And also in the description of the video it says created with visions of chaos, and then it has a link here. And it turns out there is this beautiful fractal software called Visions of Chaos, which allows you to generate a number of beautiful intricate fractals and also cellular automata. and I finally found the hint on how to implement those multi-state CAs under Software, Visions of Chaos, and then when you scroll down here are these Visions of Chaos tutorials down at the bottom. And they have this link to this 2D CA page here. And down here, this bit finally describes how a multi-state CA works in human-readable terms. And all this research took me maybe about a week. So I guess the takeaway here is to not get frustrated when you're looking for a certain algorithm or the solution to a certain problem. And also I'd like to point you to Softology's blog, which are the developers of Visions of Chaos, this beautiful fractal generator. And when you click on the cellular automata category here on their blogs, you see on the one hand they have quite some nice renderings here. On the other hand, they also have some neat suggestions for initial starting conditions or rules for cellular automata that you can try out and see which beautiful patterns you can create by using them. For example, here they provide some really neat rules for basically the exact same system we just implemented. So this is the one we just built here, the 445. So it means we have a survival if there's 4 adjacent neighbors, we have a birth if there's 4 adjacent neighbors, and we have a total number of 5 states. But also you could turn this into an amoeba with this more intricate rule, a coral, something called Jason's brain, a pyroclastic noise, and so forth and so forth. So this is really a rich field and a kind of a rabbit hole that you can go down if you are into tinkering with those systems. As always, I hope you enjoyed this. Have fun coding.